I want to come on now to discuss the properties of the state of a GBM process, beginning with its distribution. And as we discussed previously, if X is distributed as a geometric Brownian motion process with parameters mu, sigma, and initial value x0, then the distribution of time t of X is log normal, with mean log x0, that's log of the initial value of the process, plus t times mu minus sigma squared over 2. And the standard deviation is sigma root t. Let's look at some examples of the log normally distributed price process xt at various times t for a specific set of parameters. Here I'm using parameters mu equals 0, sigma equals 1, and initial value x0 equals 1. And I'm going to plot the distribution at various points in time. T equals a half, t equals 1, and t equals 2. Now, as you can see, as we progress through time, a couple of things happen. First of all, the spread in the distribution, that's the variance or standard deviation, increases. And we know that to be true because the standard deviation is sigma root t. It increases with the square root of time. But also notice that the mean of the distribution is moving to the left. It's becoming smaller. Why is that? Well, again, it's this function of t times mu minus sigma squared over 2. Mu in this case is 0. So the mean of the process is log of x0 plus t times minus sigma squared over 2. It's a negative linear function of time. And therefore, as time increases, the mean becomes smaller. We can look at a different example in which we set mu equal to 1 and sigma equal to 0.5, keeping the same initial value of 1. And let's increase the plot range so we can see what's going on. Now what's happening is that over time, the mean of the distribution is shifting upwards to the right. And the spread, that's the variance or the standard deviation, is increasing with the square root of time as before. Let's come on now to talk about the moments of the state of a GBM process, beginning with the mean. And if we take the mean of a GBM process with parameters mu, sigma, and initial value x0 at time t, it's simply x0 times e to the mu t. So the process mean is growing at a rate e to the mu t. Let's look at that state mean for different values of mu. Here we'll define a function that gives the mean of the process at time t, and we'll look at how the mean grows over time for a GBM process with different parameters, mu equal 0.1, 0.2, and 0.3. You can see the exponential growth in the mean, and of course the rate of increase accelerates for larger mu. Looking at standard deviation, we find that it equals this expression. It's the square root of x0 squared, e to the 2t mu times e to the t sigma squared minus 1. Again, we can define a function to calculate the standard deviation of a GBM process with parameters mu, sigma, and x0, setting mu equal to 0 in this case, and the initial value to 100. And let's plot that standard deviation for different values of sigma. Sigma equals 0.15, sigma equals 0.2, and again 0.3. You can see fairly clearly that the standard deviation is growing with the square root of time, and the rate of growth increases with the parameter sigma. Turning now to the higher moments, beginning with the skewness, we find that the skewness of the state of a GBM process is given by this expression, and it grows in proportion to e to the t sigma squared. Let's define a function that calculates the skewness of the GBM process at time t. And then let's have a look at the skewness at time t for a process as sigma increases from 0.15 through to 0.3. As we do that, we can see the growth in the skewness of the process in all cases, but that rate of growth accelerates as sigma increases. The kurtosis of the process state is given by the following expression. Again, we can get better understanding of the behavior of the kurtosis over time by defining a function that calculates the kurtosis and then plotting the kurtosis as t ranges from 0 to 10 for processes with sigma set to 0.15 through 0.30. Now, in all cases, the kurtosis increases over time, but the rate of growth rapidly accelerates as sigma becomes larger.